This is the device I was using to make the captures. This is ordinary Raspberry Pi, nothing funny inside it. Camera mount, thought that was quite cute. Wi-Fi dongle, made out of really tiny. Lithium battery. You get about 5 hours of that before getting down to 1 bar. It's 1 light. I think that's 5.2 amp hours. This is an RS one. They start off about 40 quid, and they came down to 32. Then they came down to 12, so I bought one. And now they've gone back up to 32. So I don't know what's happening with the price. Yes. So some sort of battery pack anyway. So as it stands, that's really an outside broadcast unit. You can feed that back into Digilite UDP, and you can move around your shack and your house or garden, or maybe around a site, and do some outside broadcasting. You can always run a viewfinder off the composite output. So quite compact.
So you can get the video out of the composite. So you're using the Pi camera, but there's a
preview in the video converter Raspberry Vid, and you can output any size as well, so you don't have to fill up your whole screen. So it seemed, being able to do that, it seemed logical to go further, because at the moment you still have to output the data to a computer to send it.
On the table, so Peter.
Yeah, sure. High-tech fasteners, of course, I didn't mention this. So you still have to output the data somewhere to transmit it. You've now got your raw transport stream. It needs to go somewhere. So why not try and build the modulator directly into the Pi, so it doesn't have to go anywhere at all, and it becomes a completely self-contained unit. We can get back to the presentation. Drink while you're doing that. Pi. You just need an amplifier, of course, but then you've done away with your computer altogether. So the first thought I had was to use 323K, but having seen what F5OEO and F60ZP are doing, maybe we can go narrow now.
You've got 15 minutes.
Okay.
15.
Thanks. So, this again is based on the same DS PIC as in the Digilite, same modulator for the moment, local oscillator. So it's really cramming the bits of the Digilite into the Pi that the Pi can't do. That's the Mark II under construction. I'll pass that around so you can have a closer look. Oh, yeah. I'll show the block diagram first. So here we have the Raspberry Pi's PCB, 26-pin header, and then on top of that directly is the Digithin PCB. Very much a work in progress, as you can see. It's quite a bit more to be put on before the Mark II is ready for testing. In fact, I'm testing as I'm going, just seeing, will it actually do this? Can I actually transfer the data? Will it actually do this, that and the other? So the data comes out of the Pi, instead of going into the Wi-Fi, it comes out on an SPI port, which is very simple, a serial port, and goes into the DS PIC. The instead of putting a crystal on the DS pick, there's a 4 meg oscillator, or there's a variable oscillator in the Pi itself. You can set one of the output pins frequency. UART, so we can there's also some spur pins coming off the 26-pin header. About 3-pin spur. You could put a local oscillator board perhaps underneath the main board. The digital filtering occurs inside the DS pick, and it outputs that to a dual digital analog converter through some analog filters. You'll always find once you've done any digital output you need to analog filter it again. Seems a contradiction, but that's the way it always is. And then into the 88345 that we use on the 77 Digilight, and the local oscillator balun. From wherever the local oscillator comes, you could have an external one or try and fit it internally. There's probably plenty of space for it. One thing came up from only a week ago. Can we do the audio on the Digithin? There's no audio input on the Raspberry Pi, which is a bit of a drawback for DATVers. You can get there's probably USB things you can input audio on, but the DS pick has digital analog converters on it, so maybe we can feed the audio straight into the DS pick, and that can send it back on one of the 2 ports and do the compression in software on the Raspberry Pi. Although I'm told the MP2, the audio compression, takes about 50% of the Pi's CPU, so how practical is it, I don't know. So we'll have to see on that one. Just a look around the board. So we've got the 26-pin connector here. I don't really like running tracks through pins, even 2.5 or 4mm pins on development boards, so I've removed some of the pins out of the connector. That's the connector on the Digithin. I haven't chopped them off the Raspberry Pi. Just taken the ones I need. So DS pick out to the dual DAC. There's an op amp here. This is the I op amp. Then there'll be a filter after the op amp. Then into the modulator, and the space here for a mimic. You can probably squeeze another mimic on there as well to get a bit more output. Same here again, another op amp and filter combination, and that's the BQ input 345. This gap here, there's a board called a Banana Pi come out fairly recently, which looks very similar, but it's got a better processor on. I think it's a dual core. Lots more facilities on, but exactly how compatible is it, I don't know. The main thing is, can it do the hardware H.264 compression? If you can't do that, then there's no point. But I left that bit there because the connector is further over, where it is supposed to be compatible. Whether it'll fit here now I've extended the board, I don't know, but that may be a possibility. Go to the Banana Pi, which has more power, then that'll do the audio for you. Just a quick word about receivers. Assuming Digithin works, we've now taken the PC out of the transmitting equation. Unfortunately, because domestic receivers don't go below 1 megasymbol, we're now back to putting a receiver card in a PC to receive it. So we shot ourselves in the foot a bit, really. So the options are PCI boards. I think these are used for TuTune quite a bit, and the ISS. There's a USB one which I haven't investigated yet. Apparently that one is the equivalent of that, so that should come down to low symbol rates. I think below 200k symbols, F50 EO said. I've got to try any receiving, so that'll be interesting. We've been lucky so far with 23 cents particularly. We can use domestic receivers, so FM and analog, FM and digital, but I think the time has probably come. We need to develop our own receivers. And maybe we can do that on SDRs, as we saw before. The SDR just presents all the processing on it. Quite a lot of work to do in it. The error correction itself has to be undone, and Reed Solomon and the Viterbi for the FEC, they're quite intensive, I would think. So there would be a lot of work there, but I think it's something we need to be looking at rather than relying on off-the-shelf things, which below 1 megasymbol won't work anymore. And if it would run on a Raspberry Pi, the Raspberry Pi has hardware MPEG-2 and H.264 decode. For the MPEG-2 you have to pay a few quid for a software license. But if you could actually build the receiver into the Raspberry Pi, you could just output it on the HDMI port. Then you've got a complete transceiver then in the Raspberry Pi. I've always tried to make things buildable by people at home, myself as well. I don't really like going below SOIC 1.27 millimeters, so this is my take on some of the smaller components. The QPSK modulator, it's not too bad because a lot of the pins are side by side connected together, so you only got to get about 4 of them right. I'm increasingly in the trembling and shaking league, so I've yet to put it on Digithin. That should be fun. There's also the BGA chip with the little solder balls at 0.6 millimeter, but I left that off. I left BGA off for reasons of good taste. So the board, you can see, it's the same level of construction as Digilite. The 1206 components, SOIC ICs, and just the modulator, which is going to be a bit tricky. So nothing too difficult there. Just a reminder of the diagram again. Time's pressing on, so digital filtering is you want to be 60 dB down at 1.35 times the frequency, so that's rather difficult for an analog filter, so you have to do it digitally. And we've all probably heard HF rigs, and we can have some amazing filters, very, very sharp, no ringing, and that's all down to DSP. Time's pressing on, so I think I'll probably skip over that quite a bit. Suffice it to say that you can get some really good filters with the DSP, and it's really down to processing power. The more power you've got, the more you can filter. Whoops. Where'd that go? This is the basis of DSP. You have an analog input waveform. You measure the voltage at various intervals, whatever, say for audio maybe 8,000 times per second. You sacrifice a few goats and do some black magic on the incoming samples, and then you output the resulting values and reconstruct the waveform, and then you've got your output again, which has got all the beeps and noise taken out of it. So if we were running at 333K symbols, we'd have 333K bits on each of I and Q, and so say it's going 0, 1, 0, 1, 0, 1, it would look like that, so that would be 166 kilohertz. So we want to be starting to roll off at 166 kilohertz and be 60 dB down at 224. It should be 3 microseconds there, not 3 milliseconds at 333K bits. But as we saw in the last slide, sometimes you can output at different rates than you input, and there are advantages in that. The higher you reconstruct the output, you can never get it quite right because you're filling in little bits and you can never get the right value. You can't have your sine wave exact, but you can get very close, but all the little bits are very high frequency jaggy bits, so they create a lot of harmonic type bits that you don't want. When you add some more samples to the incoming waveform, so let's say we're going to upsample by 4, say. So really we want 4 samples now every 3 microseconds. How do you work these samples out? Well, you could say, why not just have 3 more at the same value? Then your output rate would be 4 times what it was. That doesn't work because it causes distortion in the passband, in the band you want to filter, so that's not very good. You could say maybe put 3, 1 there, 1 there, 1 there, so you get a sort of triangular waveform. That's better, but you think of our digital as now plus 1 and minus 1. There's lots of multiplication goes on in digital filtering, so it's quite easy to multiply by plus or minus 1. You just add it. So you don't want to be introducing fractional values. So what you actually do is you sacrifice a few more goats, and all the other samples are 0. That just looks crazy. The waveform now you're giving to the filter, it was sort of symmetrical before, it's that. So that just looks like it's you'll never get it back again. We're now upsampling by 4, so the filter output will now be 4 times as great as it was. There is a parallel for this, though. It's not as crazy as it looks. If you think of a Class C amplifier, that's your input signal. It's biased just to conduct on the peaks of the waveform. Then it goes through the pi tank circuit, which is effectively a low-pass filter, takes out all the harmonic bits and reconstructs this waveform. So there is a bit of method in its madness of just putting zeros in for extra samples. Seems to work, but definitely not intuitive like a lot of DSP is. Strange stuff. I was going to go in through a bit more of the DSP stuff, but we'll leave that for now. Here's part of the black magic. You have your current samples. You've saved all your samples from probably, could even be 128 samples ago, or 256. The more, the better, but the more the processing power. And each of these is called a tap. And every time you want to output a value, you multiply what the sample was by a certain coefficient. These stay the same for any particular filter. So you might take, yes, we'll have half of that, minus 3/4 of that, and these tail off to a lower value as you go backwards. But it's, again, it's not intuitive at all. It's very strange stuff. One important thing is that it's a finite impulse response, as it's called. There's no feedback. Some digital filters, you can feed back the output value into the input, and they can actually take off. But there's no chance of that with this the finite one, because once the value's gone in, eventually it will fall off the end and have no effect at all. That's just showing how this isn't the DAC we're using. It'd be nice to use this sort of DAC, but this is one of the smaller pin variety. I think the ATV Express uses one in that family. They have balanced outputs, and the 88345 has balance, which is quite handy. Still need a bit of filtering, but in Digilight the negative is synthesized from the positive with the op-amp and doing inversion. But driving things differentially, you'll cut down any noise that's in there.
5 minutes, Mark.
Thanks. So I've been using these differential op-amps I've never used before. So you just put one value in, and you get two levels out in antiphase like this, which is quite handy. It's exactly what you want for the modulator. And there's a pin you can bias it, so you bias them to each output to 700 millivolts. Set your amplitude. You still need a 5-pole LC filter like we have on the Digilight, but now it's got to be balanced. You have to have inductors in both legs, so it's a bit has a few more components. Why do we need analog filters after digital ones? Unfortunately, it's because the digital filter acts a bit like a mixer. If, say this is our 166 kilohertz here, just this line, and we were at 333 K symbols, so we've upsampled by 4, and now we're outputting a sample to the DAC every at 1.333 megahertz. And you can see you get all this mess, these keep reappearing and appearing, lower in value, but you've still got to clean up this mess. The only bit you want is this region here. And you can see how there's an image around every multiple of the sampling frequency. So we need an analog low-pass filter to chop it way down by the time the first image appears. And it needs to be a lot more than that, minus 60 probably at that point. So you can just about do that with a 5-pole LC filter. You can see as you upsample more, if we'd upsample by 8, we'd now be sending samples out at that rate, and the low-pass filter's got a much easier job. But we've doubled, samples have doubled, so we've doubled the amount of processing power it takes to actually do that in the digital filter. So again, swings and roundabouts. You know how you have to change the filter in the Digilight. You want to be on 2 megasymbols or 4. Well, the only thing that matters here is the sampling rate. So if you keep the output sampling rate or the reconstruction rate the same, you can have different symbol rates and upsample them by a different factor. As long as you're outputting 1333K samples out of the digital filter, you don't need to change your analog filter after it. It only depends on this. So it's more easy to change symbol rate with when you have a digital filter there. I think that's about it. So probably about 1 minute left for questions, I should think.
Good. Okay. Thanks, Brian. I guess the one thing that really came out there for me was this business of the receiver. I think we've got quite a lot of transmit projects ongoing, but as we delve down to the low symbol rates, we can't use consumer receivers. We really are doing something, a common strategy on receivers. So, any other questions from the floor?
So using DVB-S, although the Germans and a few other people make a lot of noise about S2.
The Germans are using DVB-S2 rather than DVB-S. Yeah, that does give you advantages in the transmission, get you a few dB, just because the error correction is better. Of course, it's much more difficult to produce. The Viterbi, the forward error correction equivalent is, the codes like that are much more difficult to do, and Charles is better placed to, maybe he'll mention that in his talk briefly. Plus there's also, I think you need a license to use DVB-S2 to produce a DVB-S2 stream, whereas you don't seem to for DVB-S, so there are some legal problems as well.
So you're fairly happy at the moment to stay on with X, basically.
Yeah. But it would be good to do, and I'm sure people will look at it. But it takes a lot more processing power to produce it.
Any others? Yep.
In one of your slides you showed the effect of losing some of the symbols samples. In the BSK situation, is it possible to multiplex that redundancy on a time division?
I'm not quite sure I understand the question actually. Do you want to multiplex do it in time, send the same thing twice, effectively?
Yes, on a time division basis, rather than PSK.
I don't know is the short answer. There's lots of error correction built in. You get the Viterbi, which gives you 3/4 means you're using a quarter of the data for error correction. But doing a time algorithm as well spreads one packet out over a long time. So if you get a big splat there, once you rebuild the packet, then the spats appear like that rather than all in one place. Again, you'd probably have to have a special receiver to do that, and so far we've been tied to the broadcast ones, but maybe now, if we're not tied to broadcast receivers, we can look at things like that.
Okay, we're getting a bit short of time, so any more? Brian's around, so come and see him. I mean, you talked about a board. Any ideas? When?
Not at the moment. Yeah, I'd say
end of the year. I've already said to Brian that we would stock it in the BATC shop along with the pick if that helped. So watch this space. No doubt there'll be a report on the KLB show tonight. He's built 3 already. So thanks, Brian.
Okay.